Now, this chapter covers liquids, solids, and intermolecular forces. Okay, so on Thursday, there's a chapter on solids, but what I'm going to cover in this chapter on solids will do for that chapter. So I'm going to focus primarily on liquids and solutions, particularly solutions. That's a big deal for this unit. So I'm going to spend most of the time in this unit on solutions and all the quantitative relationships that go around that. Now, this intermolecular forces component is extremely important. It makes materials behave in a certain way. For example, water is a very unique compound. Water has extremely strong intermolecular forces. And because of that, it can hold more heat than other molecules, same size. It does a lot of very interesting things because of the intermolecular forces. In biochemistry, you must have studied this a lot in biochemistry, intermolecular forces. In biochemistry, organic chemistry, intermolecular forces, I call them IMFs, because intermolecular forces is a long word, especially to write it. And the IMFs are really important. And on my tests in those other classes, every test has IMF questions, just because those forces interact so much and they affect things so much. The other thing that's important about intermolecular forces they determine whether the compound is a gas, liquid, or solid. Now, intermolecular forces are attractive forces, and they're attractive forces because of the main the main intensity of the dipole within the molecule. Strong dipoles, strong intermolecular forces. So we're going to get into that in a little more detail, but basically, IMF Okay, so number one is same model to same molecule. That's a TO. In other words, if we had just a glass of water, the only thing in there is the water. But if we put something else in there, then we have a situation where we have a solute and a solvent. So the intermolecular forces are going to be directly proportional to the strength of the dipole. And then we're going to have two situations where we have just one compound or we have a mixture. And that mixture is a homogeneous mixture. Three states of matter, you're probably very comfortable with this concept. The state of matter depends on pressure, volume, temperature, okay? So changing the temperature will change the could change the state of the compound. Water, if it's below 0 degrees Celsius, it's a solid. Between 0 and 100, it's a liquid. Above 100, it's a gas. All we've done is just change the temperature, because that changes the movement of the molecule, changes the kinetic energy of the molecule. It changes, and that's a reflection of the temperature. You can see the density varies somewhat between liquid solid, but horrendous between gas and liquid. Now you can look at something called a phase diagram that reflects it better than this. There's all kinds of lines at different pressures, different temperatures. So you can determine, for example, if you want water to boil at room temperature, what must the pressure be for that to happen? So your phase diagram will tell you that. We'll show you some phase diagrams. Now, as a mechanical engineer, when you're designing systems with pumps, pipes, etc., you got to be very aware of the first two here, particularly. Okay. Both gas and liquid don't have a definite shape. They're shaped by the container from within these molecules reside. Strength of intermolecular forces, weak, moderate, strong. So because they're so far apart, they don't attract one another because of distance. Liquids, they're much closer together, so the influence of intermolecular forces is much stronger. And then, of course, solids, they're really close together, so those influences are particularly strong. Now, liquids, okay, they are closely packed together. And because they're closely packed together and they have an indefinite shape, mechanical engineers can use that to their advantage in designing systems. It's called hydraulics. Particles can move. Hence, if the shape of the container changes, the liquid inside it is going to take that shape. Now, hydraulic systems move. They usually move a cylinder. So if one cylinder changes shape on one end, at the other end, that cylinder will try to conform to the new shape of the liquid. In an hydraulic system, they jack the pressure up pretty high so that that influence is very, very tight. Now, gases, on the other hand, are not nearly as efficient at doing this as liquids. So when I was in the Air Force, I used to have to work on pneumatic systems. Pneumatic systems are air. And air is at really high temperatures. One method we used to see if there was any leaks in the line was a broom. And we'd move along the surface, and if there was a leak in the pneumatic system, the broom would be blown. It would go. So the air is very, very high temperature, or high pressure, I should say. Once it's at high pressure, it mimics a liquid. Remember, a liquid, the molecules are close together and they fill the container. Gases at super high pressure mimic a liquid. So when you have an actuator on one end, actuator on the other end with extremely high pressure air, it acts like a hydraulic system. And there are advantages and disadvantages of one over the other. I personally like liquid hydraulics. And again, gas is compressible because the distance at room temperature between gas molecule to gas molecule is very far apart. So there's a lot of room to change the volume of that gas. Sorry about my voice. It's been this way for a couple of days. Okay, so liquids will compress, but not as much as gases. Hydraulic systems, liquid hydraulic systems are under pressure just to make sure that the compressibility is minimized. Now, solids are very different than liquids. Solids are dense like liquids, but because of the crystal lattice force energy within the crystal, it will keep the crystal together because why do you think that is? What is the main reason we always talk about why things happen? Stability. Yeah, it's more stable that way. And there are two main kinds of solids. Crystalline solids, which you're most familiar with. You see rock candy, which is a crystal of sucrose, nice and angular, a diamond, salt crystals. Those are crystalline solids. And those have a definite order. And the order depends on the intermolecular force interactions between the atoms and also the geometry of the actual molecule itself and how best they fit together. Some solids don't have a structure like that. They're kind of like a blob. Glass, for example. Have you ever seen antique glass? What does antique glass look like?
Kind of cloudy.
It can be cloudy. What else? Yeah. Yeah, that's where he was going with kind of cloudy. Right. What else? What about?
Just color.
Yeah, it could be different color from when the original color. What else? Yeah. Okay, less smooth, meaning that the structure has changed. If you look at antique glass, you can go into a church with big stained glass windows that are old, or if you go to an historical building with original windows, you'll find the windows, if you look on the side, if you look at a cross section of that window pane, it's not going to be a nice uniform thickness. It gets thicker and thicker at the bottom. What do you think that is from? Yeah. Remember now, I'm old, hard of hearing, and secondly, I've got. Well, what? A tiny bit. What forces are acting on us right now? Huh? Gravity. Okay. So gravity works on everything, including glass. So one reason this is like this is because gravity is pulling down on that glass ever so slowly. Because when we look at a glass pane, it doesn't look like it's moving. But give it 100, 150 years, and it's definitely going to look like this. It's not very, the clarity is poor. In other words, when you look at it, it looks like you're squinting your eyes a little bit, or things aren't perfectly crisp when you look through it. Okay. This is what glass is. So these type of solids will move over time if there's a force acting upon it. These won't. Also in old glass, you'll see something else. You'll see tiny bubbles. And again, it's because of the movement. But the fact that it's moving takes in gas. Now, I'm not sure on plastic. There are so many different kinds of plastic. Some are more amorphous than others. So I'm not sure that's a great example. Glass is a really nice one because it's easy to observe. You can go look, visit an antique, Sutter's Fort, or some one of the gold minings up here in the foothills. You can find a lot of old buildings from that era, and they really are nice examples of amorphous solids. But plastic, there's probably 1,000 different kinds of plastic, and all of them vary a lot. So I personally don't think that's a very good example. Now, this is an important concept. When we change the temperature of a molecule, as you know, its kinetic energy changes because temperature is a metric of that kinetic energy. All right, what happens 2 different times during the temperature change, that the molecules will be more stable in either a solid arrangement, a liquid arrangement, or a gas arrangement. And those variables are PVT. So when you are changing the phase of a compound from, say, solid to liquid, the liquid molecules are moving faster. Hence, we have to apply heat. But if we're trying to move them out of a solid state that's stable, it requires energy to just get it out of the solid state into the liquid state with no temperature change, even though we're adding temperature. So there's 2 kinds of motions we have with normal compounds when we add temperature. One is the kinetic energy will increase or the state will change. When I say state, I'm talking about gas, liquid, solid. And that depends on pressure, volume, temperature. Okay, so this going from here to here is no temperature change. What we're changing instead is the structure. Now, if we keep putting heat in, gradually all the solid is going to change structure. And what do you think happens when all the solid is no longer a solid? When we keep adding heat. Hmm? Well, but just, that's right, eventually. Let's not consider it. Just right here, in this situation here. We keep adding heat. The solid starts disorganizing. That requires energy. And when you get into thermodynamics, that force is called entropy. So we're going from an organized to a disorganized state. What happens when this is all gone? It's converted from the solid to the liquid. Yeah.
Does the density change?
Density will change. What else will change?
So
Not necessarily structure. Yeah. Volume will change. What will the metric do? Yeah.
the internal energy of the molecules change as well.
Say again.
The internal energy of the molecules increase.
Yes. And how do we measure that internal?
Joules, I think.
There's an easier way. How do we measure temperature? Temperature goes up. Much simpler. You're right, but it's much simpler. Okay. And remember, temperature is a metric that that allows us to have a feel for the kinetic energy of movement of the molecule. So we go from here to here. There's no temperature change because the energy requirement is going into moving the solid phase to the liquid phase. Okay. After it's all completed, then the temperature starts going up because the energy then is manifested in the actual movement of the molecule. Now that is really important to understand that. And let's just look at solid going to liquid. So if we look at temperature, as we keep increasing temperature, that solid now is going to be converted into liquid. So in that flat portion of that graph, that flat portion of the graph is neither pure solid or pure liquid. As soon as it hits here, it's pure liquid. Yeah.
Don't you need to raise the temperature to that, the melting point of that substance first? So how did the temperature increase in order to get to that melting point?
Yes. It increases and then
Then when it's melting, then it's not.
there's no change. If you're measuring temperature. Okay, in other words, we're putting heat in there. Okay, so we're increasing the heat. Yeah. It totally depends on the liquid. excuse me, totally depends on the compound. Some is a really long period. It also depends on how much heat we're putting in. You know, if the heat curve is more steep, then we're putting in per unit time, we're putting in more energy. So that phase change is going to be smaller. If the heat change is gradual, then that is going to be a gradual conversion from all. Okay, let me make some more notes here. Okay, at that point, everything is still 100% solid. At that point, it's 100% liquid. So this energy from here to here is converting the solid to liquid. Yeah. Yeah, so it's starting to, you know, like your soft drink, got ice in it. And what happens to the ice gradually melts, right? So there's a combination of solid ice and liquid. Yeah, so those two extremes, there's a transition. As you keep putting more heat in, the transition is to more of a liquid. And the same phenomenon happens going from liquid to gas. Okay? Okay, so then the same thing would happen going from a liquid to a gas. Okay, so the temperature would go up until the transition starts. You have to keep putting more energy in though. And that more energy then is manifested in going from the gas to liquid until there's no more gas left, 100% gas, then the temperature starts going up again. So if we look at these together, and then we have, of course, the energy never stops, only the temperature plateaus. Okay, so temperature goes up. Normally when we put energy into a system, normally temperature goes up because you're putting more, becomes more kinetic energy. The metric for kinetic energy is temperature, so it keeps going, except when we're going from one phase to the other. Then that energy is spent differently. It's converting something that's more stable to something less stable, something ordered to something more random. All right. I talked about intermolecular forces very briefly. It has to do again with a dipole. If the molecules can form a dipole, the intermolecular forces will increase. If the dipole cannot form, then the intermolecular forces are very weak. And one thing, when you have a molecule, it's the sum of all the dipoles. Remember, dipoles have a force vector associated with them. So if all the vectors cancel, then the net dipole moment for that molecule is zero. Hence, it has zero intermolecular forces. Now, the interesting thing about intermolecular forces, there are three different kinds. And I'm going to talk about them in reverse order. I'm going to talk about this one last because it's the trickiest to understand. Okay, so going back to our old delta electronegativity, if it's greater than 0.4, there's a dipole formed. The closer you get to 0.4, there's a pseudo dipole. They call it a nonpolar dipole. After 0.4, it's considered a stronger dipole, all the way up to 2, which becomes ionic. Okay. Okay, so methanol. Does methanol have a net dipole? Well, remember it's got oxygen. Two single bond oxygen. So the net, we're gonna have a net dipole then. Okay, so let's see what this looks like though when we start for an intermolecular forces. Okay, so if you look up the delta En for CH, it's like 0.4. CO is going to be like 1. This is going to be like 1.4. So whenever we have a oxygen bonded by a hydrogen or a nitrogen bonded by hydrogen, that's a special kind of bond that's called hydrogen bond. the OH is stronger than the NH. So whenever hydrogen bonds to whenever hydrogen bonds to any of those three, it's considered a hydrogen bond. Now we talk about our biochemical systems. Of course, there's no fluorine in the body. So normally it's bonding to oxygen or nitrogen. But fluorine, HF gives the strongest hydrogen bond. Okay, and you can see right here, it's easier to read on mine than yours. So this methanol's got an OH bond, a very strong hydrogen bond. Okay, now that's going to overwhelm the molecule in terms of polarity. It's also got a moderately strong carbon-oxygen bond. And we have three weaklings, three weak bonds. So overall, methanol is going to be a net polar molecule. So in our description of intermolecular forces, hydrogen bonding is the strongest. Then comes we call it either a permanent dipole or a dipole-dipole. Okay, so over here, we've got the hydrogen bonding strongest, dipole-dipole, kind of medium. And then this dispersion forces. Okay, dispersion forces are kind of weird. One, all molecules and atoms have dispersion forces. No exception. What's going on is we're looking at the nucleus versus the surrounding electrons. Now, this is a diagram of helium. Helium has 2 electrons. Well, okay, the nucleus, as you know, is positive. Electrons are negative. So the relative placement of these 2 dipole forces don't cancel each other out. This one does for exactly 180, and this one doesn't. Okay? So all molecules, all atoms have electrons. They all have nuclei. So you're always going to have these little dipoles always forming in every single molecule of the atom all the time. Now there's one instance, one flash, where these are exactly opposing. Hence, there's no dipole, no net dipole. Every other time, there is one. And it's very weak. Okay, so we're talking about extremely small percentage of the time when these all cancel out, but they happen. Most of the time, there's a weak dipole. So going back to our diagram of relative strength, and all molecules, I want to accentuate that again. All molecules will have it, but they are super weak. So if I was asking you to describe the intermolecular forces of a molecule, you have to go down that list. Does it have hydrogen bonding? Does it have dipole? And does it have London dispersion forces? The other name for this is London dispersion forces, or LDF. So if I asked you for a molecule you've never seen before, what's the first thing you write down as far as intermolecular force for that molecule? Huh? Yes, London dispersion forces. Boom, LDFs. No exceptions, just right off the bat. Boom, LDF. And it may not have any other. So we looked at this methanol. Let's look at propane. Okay, so we always have to add LDF to everything. So what are the IMFs for propane now? Well, one is LDF. What else? Hydrogen bonding. What's the definition of hydrogen bonding?
Oh, to an O and an F.
Right. It's got to be bonded to an O, N, or an F. It's not hydrogen bonding. That makes sense? Okay, what other IMFs do we have? Well, we've got 8 CHs, right? A C-8 is a 0.4 delta En. So those are slightly polar, but not much. So what else do we have? Nothing else. So the only intermolecular forces on propane is a dispersion force, the London dispersion forces. So overall, which has stronger IMFs, the methanol or the propane? Methanol. Now, IMFs are attractive because an IMF is a dipole, and dipoles are attracted to other dipoles. Yeah.
I might have missed if you said this, but how you find if it's a permanent dipole?
If it's 0.4 or greater.
Uh,
And they call that dipole-dipole. Okay, so IMFs, period, no exceptions, are attracted to another molecule with IMFs. Okay, so if you have strong IMF, you have strong attraction. Conversely, weak IMF, weak attraction. Now let's look at something interesting. If we were going to boil something, what is boiling?
Raising temperature,
Right? And what's the physical manifestation of that?
causing the molecules to move faster,
Faster, except during,
transition.
yeah, exactly. So what were you going to say?
I was gonna say like, when the liquids like start changing to gas.
Turning to gas or phase change. Okay, so does it take more energy to put a molecule in the air if it's strongly attached to another molecule or weakly attached to another molecule? Which requires more energy?
Strong.
Hmm?
Strong.
Strong, exactly. That's what you just said, right? Okay, sorry, my hearing is, okay. So if it's strongly attracted, it takes more energy to break them apart to move from the liquid into the gas phase. Okay. This is a real important deal. So if there's a strong intermolecular force, it takes a higher temperature to change phases because they're more attracted to one another. And conversely, if you have a if you have weak IMF, weak attractiveness requires less energy to move it to another state. Okay. So we're looking at propane only has LDF. Methanol has LDF, dipole-dipole, and hydrogen bonding. If you look at the boiling point for methanol versus propane, propane's a gas. It's already been boiled. Methanol comes in a container. It's a liquid. That's why it's a liquid, because the intermolecular force is so strong. They're attracted together strongly. Okay, does that make sense? The stronger the IMF, the higher the melting point, the higher the boiling point. Think of that as stickiness. That is Ferguson's term for So the stickier the molecules or atoms are, takes more energy to pull them apart. Okay. That's why intermolecular force understanding is really important. Does that make sense? Are there any? Okay. Now I have a story. Who remembers the Lone Ranger? Okay. Anyone not know who Lone Ranger is? Lone Ranger and Tonto. Okay. Lone Ranger was kind of arrogant, kind of a know-it-all. Typical guy with a doesn't want to show his face. Okay. And he thought he knew it all. Well, Tonto, Native American, I'm Cherokee, Native American. He was trying to illustrate to the Lone Ranger about forces. So he gives the Lone Ranger an arrow. And he said, break it. The Lone Ranger goes, breaks it in half. Tonto gives him 2 arrows. Let's break it. Breaks it in half. Then Tonto gives them a whole quiver of arrows. Lone Ranger cannot break it. Okay. It takes a very weak force to break 1 arrow. But when you get a whole bunch of them together, collectively, they net a very strong force, which is a nice perspective from a political point of view. If you've got a few very strong players versus a whole bunch of weak players, collectively, they can change things. Exactly what happens with weak versus strong in molecular forces. That's what they're talking about here. So the more LDFs, collectively, the stronger the net IMF for the molecule. So let me give you some examples of that. Okay, so we have 2-carbon ethane, 6-carbon hexane. Okay, so looking at the intermolecular forces for these 2 molecules, automatically, what do they have? LDF, boom. Okay, just right out of your mouth, LDF. What else? Well, we've got the CH bond, right? Is that considered a dipole-dipole IMF? Slightly, not enough to say much about. So the CH really doesn't count. It's close, but it doesn't count. So the only IMF in these 2 molecules is London dispersion forces. Which is stronger? Now you have to look collectively at the individual IMFs.
There's more HC than hexane.
Yeah, so we have more weak LDFs. Remember, every atom has got an LDF. So this has more atoms, so more LDFs than this. we have those so we have okay, so we have 8 LDFs, 20 LDFs. So the more LDFs, yeah,
How do you?
an individual atom. So count the atoms. So here we have 6 carbons, 14 hydrogens. And LDFs vary depending on how many electrons are there, how they're shielding one another. There's a whole bunch of variables, but basically an IDF, London dispersion force. And then in the hexane, we've got significantly more carbon hydrogen bonds. And what's the delta EN for CC? 0. 0. So it's a pure covalent. Pure covalents have absolutely no delta EN. Okay, so which has a higher boiling point? The hexane or the ethane? Higher boiling point. Which one requires more energy to get into gas? The answer to that is, think about IMFs. Which has more IMFs? Hexane, hence it's got a higher boiling point. Also got a higher melting point. So ethane is a gas. Hexane is a liquid. You can buy hexane at the store and you buy ethane at the store. Hexane comes in a can because it's a liquid. That means its boiling point is much higher than the ethane. Ethane's already been boiled away, gas. The mass also determines boiling point. Something heavier takes more energy to get into the gas phase. Something super light just goes right in. So mass is directly proportional as well. Now this is something interesting. Each of these have 5 carbons. If you can lay these So this long string, the N stands for normal. Normal means long string, no branching. So look at the contact points this has versus this one. More contact points, that means that more dipole-dipole interactions, more attractiveness, more stickiness. That means the long skinny one can lie side by side and get all these contacts versus one that's branched, which only has 2 contact points. Hence, this requires more energy. It has more sticky points than this one. So this is going to have a higher boiling point. Okay, so we move on here. So if we're looking at the same kind of structure, long, skinny, no branching, as the mass increases, the boiling point increases. Branch has less stickiness than straight chain because it has less interactive points. Oh. Oh. Okay, I tell you what, I'm going to end this today right here.